Will be my presentation for the machine learning class final exam, and I've chosen the paper Augmenting Naive Bayes Classifier with Statistical Language Models. So we will look at the outline of the presentation, which will be the introduction and then the materials and methods, which have two separate materials and methods. First one is the naive Bayes text classifier, and then the statistical n-gram language modeling, and then finally how the statistical n-gram language modeling is applied to text classifiers. Then we'll see the results, some implications, and the conclusion, and the final acknowledgement. So the introduction: out of all machine learning models for text classification from the time the paper was written, such as Bayes classifier, SVMs, linear least square models, neural networks, and KNN, naive Bayes classifiers have been the most effective. And research has shown that violating, that is like relaxing the independence assumption that we have in naive Bayes classifier, allows for them to achieve better performance when it comes to text classification. So this is going to be the base of the paper for the authors, and they talk about another method, which is the tree augmented naive Bayes classifier, or TAN, which makes use of a tree structured dependency. So we are violating the independence assumption and making a tree structured dependency among the observed variables, along with the traditional hidden root variable dependence. But this model is rarely used in text classification. Thus, the authors propose a simplified version of TAN called Chain Augmented Naive Bayes, or CAN model, making use of a Markov chain dependency instead of a tree. The results that the authors show closely relate to n-gram language, and thus n-gram language modeling techniques were applied to CAN. The final model allows for the use of advanced smoothing techniques, which we will see later in the slides, and also achieving language and task independence. So the materials and methods: first we will see the naive Bayes text classifier that the authors introduce. So in text classification, it's the problem of assigning a document D to a set of C predefined categories, where C is equal to C1 to CC. It's the number of categories we have, making use of an algorithm where P of C given D is equal to uh, the probability of C times probability of D given C divided by probability of D. This is the normal naive Bayes, where D and C are instances from the set D and C, which is the document and the predefined category. And P of D in the denominator of the algorithm is just the sum of from all the categories for C in capital C, probability of C, probability of D given C, so the marginal. So here document D is normally represented by a vector of k attributes, so we can write it D equal to V1 to Vk, where k is a vast number. It's going to be a big number. Thus Bayes rule is applied for simplifying the equation that we saw above to probability of C given D is equal to probability of C times the product from j equal to 1 to k, probability of Vj, which is the vector representing the document, given C, divided by probability of D, by assuming independence between the attributes. That is, some V of I and V of j will not be like equal to each other. They'll be independent of each other. So this is the main assumption of naive Bayes text classifier for a given category C. Finally, MAP classifier, the maximizing, is used to find the optimal category mathematically, given as C star equal to argmax of category C belonging in capital C, the probability of C given D. So we're just maximizing the algorithm. which is equal to argmax of probability of C times the product of j equal to 1 to k, probability of V of j given C, where we drop the denominator because it is constant for every single category that we're trying to find the optimal category for. So that is dropped in the MAP classifier. And a uniform distribution or an empirical distribution, if we have enough training data, is used as the prior. And the empirical distribution is estimated with sample frequencies. So both of this, either the uniform or the empirical, can be used for the prior distribution. Next, continuing on the naive Bayes text classifier, the authors make use of a multinomial naive Bayes classifier given by uh, capital theta equal to theta jc equal, which is probability of Vj given C, where j ranges from 1 to k and 3 ranges from 1 to capital C, the categories, I'm sorry. The likelihood of a given set of documents d power c for a category C is given by probability of d power c given capital theta equal to n power c factorial divided by the product for j and jc factorial times product of j theta jc to the power of n jc, where n j to the power c is the frequency of the attribute j occurring in d power c, and n power c is the summation in all j n j power c. Maximum likelihood estimate for this yields theta jc equal to n j to the power c divided by n to the power c, where because we don't want the denominator to reach 0, we apply Laplace smoothing, resulting in a small constant aj being applied to the numerator and a constant a, which is the summation of all aj. So this is the normal naive Bayes text classifier that's been used for categorizing documents into specific categories. Next, we will see the statistical n-gram language modeling. So in language modeling, the goal is to predict the probability of natural word sequences, that is, assign high probability to more frequent words. The goal is achieved when a low perplexity, given by the formula shown here, is obtained. And the most simplest and successful basis for is the n-gram model. It's the most basic model, where the model approximates the probability of the words, so w1 to wt, equal to the product of I ranging from 1 to t, probability of I given the previous words, so the words I given word 1 to word I minus 1, by assuming that the only words relevant to predict the probability of word I given word 1 to word I minus 1 are the previous n minus 1 words. So this is the Markov n-gram independence assumption. And it is given as probability of the word I given the word 1 to word I minus 1 is equal to probability of the word I given word of I minus n plus 1 till word of I minus 1. So we are just applying the Markov n-gram independence assumption here. So a straightforward maximum likelihood estimate, we are doing a similar thing that we did for the naive Bayes. So a maximum likelihood estimate for the statistical n-gram language modeling uses the ratio of the number of occurrence of a specific n-gram in the training corpus to the entire training corpus. But this is computationally inefficient as the size of the vocabulary W increases. So also, this is also backed up by Zipf's law, which states that in a set of measured values sorted in descending order of their rank, the value of the nth entry is often approximately inversely proportional to n. So this also backs up the previous statement that we made in the last point. So one is likely to encounter novel n-grams during training. Continuing on that, the authors choose a back-off estimator to solve this problem with the problem a sparse data problem and to cope with potentially missing n-grams so we don't encounter novel n-grams during training. For simplicity's sake, its back-off estimators was the most straightforward and easiest estimator than the others that the authors show in the paper, and it is given as such. So PWI given WI minus 1, I minus n plus 1, I'm sorry, till WI minus 1 will take the value of P cap WI given WI minus n plus 1 till WI minus 1 if the number of occurrences, which is given by hash of WI minus n plus 1 till WI is greater than 0, or we are going to assign the value beta of WI minus n plus 1 till WI minus 1 times the initial value of WI given WI minus n plus 2 till WI minus 1. So what does the first part of the case mean? The cap P, it's simply the discounted probability, and in the second case the beta is a normalized constant. So this is how a back-off estimator is applied to solve the vocabulary size problem that we have here. So an n-gram is first matched against the language model to see if it has been observed in the training corpus. If that fails, the n-gram is then reduced to an n minus 1 gram by shortening the context by one word. Okay, so how is this applied to the text classifiers? So since text classifiers and n-gram models capture similar regularities, the authors combined them to in the initial equation for the naive Bayes classifier, which is C star equal to argmax C given C belonging to the capital C probability of C given D, which they expand as such, and now they use the formula that we saw in the n-gram model for probability of D given C, and then we just apply the argmax, where probability of D given C is the likelihood that an instance D from the document under a category C, which can be computed by an n-gram language model, and the prior, which can be estimated from the training data using a back-off model estimate that we just saw in the previous slide. So that was the main formula for the paper. Thus, the uh, approach author's approach is overall is to learn a separate back-off language model for each category by training on a data set from that category. This is a labeled data set. Then to categorize a new text D, they supply D to each language model, evaluate the likelihood of D under that model, and pick the winning category. So this is how the text is classified. Sorry. The authors refer to this n-gram augmented naive Bayes classifier as a chain augmented naive Bayes classifier, or CAN, as we saw in the introduction. The model does not incorporate an explicit feature selector procedure. Instead, it considers all possible n-grams as features, and their importance is implicitly considered by their contribution to the quality of language modeling. And the back-off smoothing that we saw technique effectively deals with the feature explosion problem that we might encounter and the subsequent overfitting problem that might be encountered as well. So the results, the authors test the reliability of the model on various character level and word level classification problems in various languages. So first, the authors test authorship attribution. The authors obtain an accuracy of 90% when using a character level model. So this sees every single character in the text to classify it with the n-gram n equal to 3 and absolute smoothening. So the authors state various smoothenings in the paper, such as absolute smoothening, Laplace smoothening, and the results are done for every single smoothening models, and the best one is compared with the SOTA of that time, the state of the art. And the state of the art at that time for authorship attribution was 72%. So the authors show an 18 percent point increase. On a word level model, performance increases to 96 percentage. And the next result that they show is text genre classification, where an accuracy of 86 percentage is obtained when using a character level model with bigram or n equal to 2, showing an increase of 4 percentile point from previous state of the art. And unlike previous results in text genre classification, word level models do not show a big improvement on uh, in accuracy and reaching only an accuracy of 81%. So next, the authors talk about topic detection, that is text categorization on different languages is done to show language independence of the author's model. And the authors test on English, Japanese, and Chinese datasets, obtaining a performance improvement from the previous state of the art of 1.4 percentage point to 2.6 percentage point for the English dataset. Same performance for the Japanese, so 0% point for the Japanese dataset, and 4.7 percentage point for the Chinese dataset. When using a character level model, which is more effective than a word level model for the latter two languages, which is Japanese and Chinese, which combines characters in their sentences, so character level was more effective than word level. And topic detection is also done on the Reuters 21578 dataset, which unlike these binary classification datasets is different. It's a multi-way classification dataset, which means each document is allowed to belong to more than one category. Following the previous research experiment setting, the authors reach an accuracy of 80.32 percentage. However, previous research obtained an accuracy of 92 percentage when using an SVM classifier with an optimized prior. So they are optimizing the prior on the training data. But the authors just make use of a uniform data, and so for the Reuters dataset they were not able to get higher accuracy, but they do attribute that the previous state of the art SVM classifier is much more complex than their CAN base model. Following up on the results, the authors note that their model achieves higher accuracy than previous models, although being simplistic. Thus, they analyze the various factors of their model that can contribute to this increased classification performance. So they showed the relationship between accuracy and perplexity, where a lower accuracy might be better, but it does not always mean it can lead to better decisions in the categorization accuracy. And the effect of n-gram, they see that for Western languages, a higher context is better, but for Asian languages, a lower one performs better. And for smoothening, they found that Laplace overfits, but other smoothening techniques are very similar in performance. And training size, they found that bigger training size is better, but we need a more balanced training size, not an imbalanced bigger training data. And the choice of prior, they saw that there's significant improvement for unigram models when using an empirical instead of a uniform prior. However, the difference becomes smaller and eventually can be ignored in higher order models like bigram, trigram. And for character level and word level, for Asian languages where word segmentation is hard, character level can base performs better. But for Western languages like in informal text such as newsgroup data, character level performs better. But in authorship attribution, movie review sentiment classification, word level performs better. Usually the higher n-gram word levels as well. So the implications and conclusion of the paper. The proposed model is able to work at either the character level or the word level, which provides language independence to handle various Asian and Western languages. With the authors note that the model is robust to perturbations and achieves better accuracy than previous state-of-the-arts despite the simplicity of the model. Another implication is that we need labeled training dataset for good performance, and so this is one of the main, let's say, drawback of the modeling is that we need label training dataset. And finally, the acknowledgement for this whole class for the semester. I respectfully thank Professor Negi Kang for the machine learning class, for teaching us the fundamentals, the real basics which helps us in our research, and for providing guidance throughout the course. Your support is greatly appreciated, Professor. Thank you for this class. And with that, I'll finish my presentation for the final term. Thank you.